in its entirety. I've kind of got it up here on a PowerPoint, but this is a huge part of the AP exam. You have got to go between F prime and F double prime all kinds of different ways. Whether they give you the graph of F prime and ask you things about the function, or whether they give you the graph of F prime and ask you things about the second derivative, we've got to be able to go back and forth. Now, here's what I do, and I'm going to do this right now, and my students, we write this on the board quite a few times, and I expect them to know what I'm about to write up here. If F double prime of X is positive, what does this tell me about F prime? Anybody know that? It tells me the graph of F prime is increasing, is what that tells me, which tells me the graph of F is what? Something about concavity. What'd you say? Concave up. Very good. And the graph of F is concave up. Okay? We have got to understand this very well. And then the second part of that, of course, if F double prime is negative, then that tells me that F prime of X is decreasing, which tells me that F is going to be concave down. Okay? So you've got to know that very well. Okay? This is very important. And I know these first couple of sheets here talk a little bit about that. You know, look at that first part, that first row. F prime is positive. That means F of X is increasing. Okay? F prime is negative, means F is decreasing. It goes on and talks about several things there. Then it talks about the second derivative down there towards the bottom. Second derivative is positive. That means F is concave up. Second derivative is negative, means F is concave down. And then the other part of that, though, is this part here. Not only do we need to know that if the second derivative is positive, that F is concave up, but we also need to understand that means that F prime is increasing. So if I gave you a graph of this, I'm just going to make one up before we get into the packet here. If I tell you that this is the graph of F prime, and I want you to go through and I want you to tell me where F is increasing. If this is the graph of F prime of X, and I'm going to label some values. There's A, B, this is the origin, this is C, and this is D. If I ask you right now to tell me where F of X is going to be increasing, what would you say? This is the graph of F prime. Where is F increasing?
From points A to point D.
Okay, from A to D. Okay, and how did you get that answer?
Because it's above the x-axis.
Okay, all right, very good. And I want to say one thing. In my class, I never allow my students to say it. Okay, might as well put SH in front of it. Okay, it. What is it? Okay, we have no clue what it is. All right, so we want to be very specific about what we say. Okay, because I've graded the AP exam. When you get in there and you start reading and just look at the justifications people put on there, you've got to be very specific in what you're saying. The graph, the it, general terms there are not going to get you credit. So we want to say, if I ask you to tell me where F is increasing, you would say that F is increasing from A to D because F prime is positive. Okay, we go with that? So be very specific. And then the other part of that, where would F be decreasing? F would be decreasing when F prime is negative. So where is F prime negative? From negative infinity to A and from D to infinity. Y'all, you're good with that? Now, what about relative extrema? How do you find where relative max and mins occur? If I give you the graph of F prime, and I want to know where the relative maximum would be, where do we have relative maximums? When F prime does what?
Crosses the x-axis.
Okay, that's a possible place. Okay, that's a start, but that could also be a min, couldn't it? How do you know if it's a relative max or a relative min? Ooh, you said it. All right, but you're right. When F prime changes from positive to negative. Very good. So looking up here, where would we have a relative maximum? At what value would we have a relative max?
A.
Not A. All right. At A, we're changing from negative values to positive values. So that's going to have a relative minimum at A, right? Where are we changing from being positive to being negative? At D. So at D, we would have a relative maximum. A, we would have a relative minimum. Okay, you all understand that? All right, how about this? Still graph of f prime. Where would f be concave up? Where would my function be concave up? And it helps you look up here. Where is f going to be concave up? F is going to be concave up when either the second derivative is positive or the first derivative is increasing. What are we given right here? What is this? First derivative. So what am I looking for here if I'm trying to figure out where f is concave up? I'm looking to see where f prime is what?
Increasing.
Increasing. So where is f prime here going to be increasing?
Negative infinity to b.
Negative infinity to b. Okay, very good. 0 to c. Okay, those will be the two places or the two intervals where we're concave up. And then of course the flip side of that, where is f prime decreasing? B to 0, and where else? C to infinity. So where f prime, and that's, my students struggle with this a little bit, it's a difference in saying f prime is positive and f prime is increasing, right? Where is f prime positive? Tell me that again. Where is f prime positive? A to D. Okay? Where is f prime increasing? Negative infinity to b, and from 0 to c. Okay? And then where would we, of course, be concave down? Would be concave down when f prime is doing what? Decreasing, which would be from b to 0 and from c to infinity is what we get. How about points of inflection? What are points of inflection, first of all?
We're concave.
Very good. Where we change concavity is what it is. Very good. So where would we have, what x coordinates would we have points of inflection here?
B.
What'd you say?
I said B.
Very good.
And the origin.
Okay, 0. Okay,
And C.
and c. And I always try to get my students to remember this because these questions are going to be asked a bunch of different ways. If I give you f prime and you want to find where your points of inflection are, they're going to be at the relative extrema on the graph of f prime. At those x coordinates, b, 0, and c, that's where we're going to have points of inflection. Okay? So very important that we make this connection. All right, let me do this to you. Okay, watch this now. All right, I'm going to change this. Now this graph is f double prime. This is the graph of the second derivative now, and I'm going to ask you some questions. Where would f be concave up now? Where would my graph of f be concave up? Okay, from A to D. Is that what you said? Very good. Because what are we looking for here? If this is the graph of the second derivative, we're looking to see when the second derivative is positive. Okay, look back up here. When the second derivative is positive, that means our graph is concave up. If this is the second derivative, we're looking to see when it's positive above the x-axis. And then of course the other side of that, where would we be concave down? Well, when f double prime is negative. Where would my points of inflection here be? If this is my second derivative, where would the points of inflection be for f? Come on guys, wake up, man. Breakfast too good for you? You ready to go to sleep? Again? Where would we have points of inflection?
A, 0, and C.
Okay, A and D. All right, close on the 0, but at 0, did we change concavity? What was the concavity to the left of 0 if this is the second derivative? It's positive, right? What's the second derivative to the right of 0? It's still positive, so we don't have a point of inflection at 0. But the second derivative is 0 there, but we don't change concavity. This is the big deal. Okay? So this is a huge part of AP calculus. Now, we talked at the end of our last section about position, velocity, and acceleration. It's the same thing. What's the second derivative? What would we interpret that as?
Acceleration.
Acceleration. What's our first derivative?
Velocity.
Velocity. And our function?
Position.
Position. It's the same concept, it's just asking it in a different way. Alright, so let's look at page 28. Quit talking and wake you guys up. I want you to do the first 3 questions there on page 28. out here, right? 1, 2, 3, 4. Come on, guys, I gotta hold up one number, okay? Should be 4, that's what it should be. D, that's what we should have. How about 2, what'd you get? 1, 2, 3, 4. Should be 4, that's what it should be. And then 3, how about 3? Okay. 2 should be B. Alright. Alright, let's look at number 1. Let's just, it says calculator active, but there's no calculator needed here. And that's a good thing to know. As we said just a moment ago, you're going to have 15 questions on the multiple choice with calculator. Out of those 15 questions, probably 6 of those, most years, are going to require you to use a calculator. The other 9 really are not. So just because it's on the calculator active section doesn't necessarily mean that you've got to use your calculator. So it says the temperature of a room in degrees Fahrenheit is modeled by H, a differential function of the number of minutes after the thermostat is adjusted. Of the following, which is the best interpretation of H prime of 5 equals 2? So if H here is giving me the temperature of the room at any time, if we take the derivative of H, what is that telling me? When we take a derivative, what are we doing? And I'm embarrassed to say, I attended Georgia Tech and I took calculus there. We were on the quarter system. And I got through with Cal 1 and I could take derivatives all day long. But if you asked me what a derivative was, I didn't know. I knew the derivative of sine x was cosine x. I knew a bunch of things. I didn't really know what a derivative was. But I know when my students are going to leave my classroom, when we take the derivative, what are we doing?
Looking at the slope of the original function.
Okay.
Looking at rate of change.
Okay. Looking at the instantaneous rate of change, right? I know next class y'all are going to have, you're going to talk about the mean value theorem. What's the mean value theorem say? Y'all remember that? I tell you, if the function is continuous and differentiable, then A rock's got to equal I rock. Okay, and what's I rock stand for? Instantaneous rate of change. That's the derivative. When I ask my students this all the time, what's the derivative? Well, it's the instantaneous rate of change. It's the slope of the function at a point. It's the slope of the tangent line is another way we can say it. Okay? So when we take the derivative of H, it's giving me the instantaneous rate of change of H. So it's telling me how fast is the temperature of the room changing at T equal 5. That's what it's telling me. And it tells me in this case that how fast is it changing? What's this mean? The temperature in the room at 5 hours is changing at what? 2, whatever our units are here. What are our units? Degrees Fahrenheit per what?
Minute.
Per minute? Okay, per minute. So which of these is the best choice? We said it was D. The temperature of the room is increasing. Since the derivative is positive, it's increasing at a rate of 2 degrees Fahrenheit per minute 5 minutes after the thermostat is adjusted. Okay, that's what we're saying there. And then the same thing here in number 2, it's just a different setup. We're talking about shredding paper, is what we're talking about here on number 2. We're given a cost, what happened there? We're given a cost function is what we're given of the following, which is the best interpretation of C prime of 500 equals 80. Well, it's telling me here the cost to shred the documents is increasing at $80 per pound when the weight of the documents is 500 pounds. So it's giving me the rate, the IROC, the instantaneous rate of change. How fast is that cost changing at T equal 5, or in this case, when the weight is 500 is what it's asking. Okay, so just got to know a little bit about that. And then 3, we kind of talked about this just a moment ago. Which of the 5 points on the figure at the right are dy dx? What's dy dx represent? What's that talk about? First derivative. And the second notation we have here is talking about the second derivative. We want to know where are they both negative. So if our first derivative is negative, what does that mean the function has to be doing? Decreasing. Got to be decreasing, okay? So we're done with A, we're done with D, we're done with E. It's either B or C right now. These are the only 2 places up here where that function is decreasing. And if the second derivative is negative as well, what does that mean about the function? It's got to be concave down. So if we're decreasing and concave down, B or C, which of those choices would you choose? Hopefully you would choose B. That's concave down. C there, we're concave up is what we get there. All right, I want to skip over just a little bit. I want to make sure we get to some pre-response. I want you to turn to page 36 right now. turn to page 36. We'll come back and we'll work some multiple choice in just a minute, but I want to get to several free responses. We didn't get to any just a moment ago. I want you to do that question, parts A and B, on page 36. Page 36, questions. I know that's something, if you're a true mathematician, a lot of us probably don't like to write a whole lot. We like to be able to find the solution and be done with it. But on the AP exam, you're probably going to get 10 to 12 points most year on the free response about how you justify your answer. Okay, so it's very important that we know how to justify our answers. So we have given graph of f prime. We're told that f is differentiable on this closed interval, and we're also knowing here that f of -2 is 7. The graph of f prime, the derivative of f, consists of a semicircle and 3 line segments shown above. Part B, on what intervals is f increasing? Justify your answer. Okay, very similar to the question we just worked, just a different looking graph up here. But what did we say there? Where is f going to be increasing if this is the graph of f prime? On what intervals?
-6 to -2.
-6 to -2. Very good.
And from 2 to 5.
And from 2 to 5. Okay, very good. And I don't know how your teachers talk to you about endpoints. That's a big problem in AP Calculus, whether we include endpoints or not on intervals where it's increasing, decreasing. I tell my students, we don't include the endpoints. You do what your teacher tells you. They'll give you credit either way, provided that it actually is increasing at the endpoints. But I'm always going to write it like that. How do y'all write it? You know, open intervals. Y'all do open or closed? Just depends. Open. Okay. All right. So this is where it's increasing. Now, the justifying your answer. Okay. If this is the free response question, this is going to be 1 point. This is our other point. So what are we going to write here? How are we going to justify this answer? What are we going to say? And you don't have to write a paragraph. You just got to know, let that reader know you know what's going on. How do we know that that's increasing on that interval? Because what?
If the function is above the x-axis on that interval.
If the graph of x prime is above the x-axis.
Okay. Okay, I'm not sure. Maybe you get that, but we can say it even cleaner than that. All we got to say is what? F prime is positive. That's it. Okay? So we really don't want to talk about the graph and things like that. We just want to say f prime is positive on that interval. Okay? If f prime is positive on those intervals, then we know that f is increasing. So that's all we need to write. 1 and 1. That's 2 points right there. Tell my students that's almost like getting 2 multiple choice questions correct. Not quite, because multiple choice are weighted a little bit more. They're a little bit greater than a point apiece. But anyway. All right, how about part D? It says find for each f double prime -5 and f double prime of 3, find the value, explain why it does not exist. All right, so we're wanting to find the value of the second derivative at -5. 1, 2, 3, 4, 5. There's -5 right there. We're wanting to find the value of the second derivative at -5. How do we do that? Huh?
I said number line analysis.
Number line, I'm sorry.
Number line analysis.
Number line analysis. Not sure about that. Good thought. What are we giving up here? What's this a graph of? F prime. And we're wanting to know the value of f double prime at -5. So I just want to know, we talked a minute, I want to know the value of the derivative of this graph at -5. Or in other words, I want to know how fast, what's the IROC at that point right there. That's all we're wanting to know. At -5, how fast is my function changing at that value? And what happens, what's going on, what do we see at -5? That is what type of function, this graph there?
Linear.
That's a linear function, isn't it? So we can find the slope of that line right there, correct? If we have a point at -6, 2, we got a point right there at -2. If I find the slope between these 2 points, I'm just down 2 over 4. The slope of that line there is -2. So at any point here, whether I pick any of these points right in there, we know the value of the second derivative at every point between -6 and -2 is going to be -2 because it's a linear function. Y'all follow that? Y'all wake up. We may need to stand and stretch, do some jumping jacks. We good? Y'all not excited about some calculus?
This negative one,
Ma'am?
-1.
Yeah, I was just seeing if anybody was paying attention. It's -1/2. Thank you, Ms. Igdon. All right? Actually, I wasn't. I made a mistake. All right? I make a bunch of them. Thank you. We're down
They might
to
have thought
over
it.
4. Ma'am?
Maybe they thought it and just didn't want to say it.
I got you. I bet that was it. So it's -1/2, right? We're down 2 and over a 4. All right? I forgot the slope rule there. Thank you. All right? So it's -1/2 is what we find out there. Okay? What about the value of the second derivative at 3?
It doesn't exist.
It does not exist. You're exactly right. Okay? And then it says find the value or explain why it does not exist. Why are you going to tell me that the second derivative there does not exist at 3?
Because at 3 on the first derivative graph, it forms a corner.
Okay, very good. Okay? You know, I'll just say we have a, a cusp there or a corner, whatever you want to say there. That's exactly right. We've got a sudden change in the graph, therefore the second derivative is not going to exist there. So that'd be 4 points there that we would hopefully be able to get. Okay, questions there? All right, flip the page. Do the next one, page 37. We got 3 parts here. Free response portion of the AP exam. Now, as you get into second semester, the other part of this question that's not asked was dealing with this area issue. We'll talk about that later. So part A says find all the x coordinates at which f has a relative max and give a reason for your answer. Well, we have relative maximums. We talked about that a moment ago, where f prime does what? Changes from
Increasing all the
not increasing to decreasing, but changes from positive to negative. Okay, so if this is the graph of f prime, and I know I was just talking to Ms. Higdon about, you know, using a number line, f prime is positive right there, correct? And then f prime is going to be negative when it's below the axis. So if I was to do that, that's what it would look like. If I drew a number line, and some of you may want to talk about a number line, that's fine. If you want to interpret that as a number line, if this is -2 right here, f prime is positive over here, and then all the way to 1, all right, it's 0 at 1, but then it's still negative over here all the way to 4. So if you want to talk about a number line, that's fine, I don't care. But we're looking to find out here where f prime changes from positive to negative. And hopefully we would say that that's going to be at x equals -2. That's where we're going to have a relative max. So we'd say at x equal -2, and then what about this last part? That's going to be a point for this. How do we know we have a relative max there? What would we say? Because f prime changes from what? Positive to negative. And that's enough, okay? We've shown the reader, I know why I've chosen -2. Any questions on that? Part B wants us to go and talk about, in part B, it wants us to figure out on what interval here is the graph of f going to be both concave down and decreasing. So in this part right here, in part B, we want to know where is f going to be concave down and decreasing. So what are we looking for here? All right, if this is what we're looking for, where f is concave down and decreasing, if I'm given the graph of f prime, f is decreasing when what?
F prime is negative.
F prime is negative. So I'm going to outline that again here. F prime is negative, we just talked about on this interval right here. So that's part of the characteristic we got to have. But it also wants f here to be concave down. So not only does f prime here have to be negative, but f prime also has to be doing what? Decreasing. All right? So now we've got to analyze where are we negative, which is green, and where are we decreasing? Well, it's going to be here we're decreasing, and here we're decreasing. So in part B, our answer is going to be from -2 to -1, and then from 1 to 3. And I'm pretty sure, I don't see the answer right here, but I'm pretty sure it says justify your answer or something like that, doesn't it? What does it say?
Justify.
Give a reason for that answer. Okay, so what are we going to say? What's our reason for this answer? We're looking to...
Negative and decreasing.
Very good. F prime is negative and decreasing. And that's enough right there to get those points. Okay? Everybody get it? And then the last part, part C, let me see what C says. The last part says, find the x-coordinate of all points of inflection on the graph of f and give a reason for your answer. So in part C, we want to find all our points of inflection. So where do we have points of inflection again? We said that at the beginning. There's a couple ways to say it. We have points of inflection when?
When concavity
What's that?
changes. When concavity changes.
When concavity changes, very good. So that when, what else? How's another way I can say that? When f prime,
Changes.
Has an absolute, or relative extrema.
very good. That's the way I like to remember it. Or I think you were about to say there, but what were you about to say? When f prime does what?
Changes from increasing to decreasing.
Or vice versa, or decreasing to increasing. Very good. So if this is the graph of f prime again, we want to know where we change from decreasing to increasing. So we're going to have a point of inflection at x equals -1. Now it goes from increasing to decreasing, so we're going to have another one at x equals 1. Then it goes from decreasing to increasing, we're going to have another one at 3. So we would have 3 places here where we would have points of inflection, -1, 1, and 3. And then it says, once again, give a reason for our answer. A couple different ways there. You know, what I would say is, what the last way we said, f prime changes from increasing to decreasing or vice versa. Changes from increasing to decreasing or decreasing to increasing. Okay?
Can you just say the slope of f prime changes around these points?
The slope of f prime. Okay. All right. I think you'd have to be a little more specific. You'd have to say the slope of f prime changes from positive to negative or negative to positive. I think they would give that to you. Okay. I think that would work. Okay. But we want to be real specific in our justifications. Okay. I know sometimes it's hard to get all the points as specific as they want us to be. Any questions on those 3? All right, let's do one more free response here and we'll go back and hit some multiple choice. Flip to the next page, let's do 38. You can see how many of these free response questions we're looking at here. This is a common free response question where they're giving you f prime and you've got to go through and find all this stuff out. Cater folks, I think they're gonna get up here and run out of here now, don't you? Teachers done left.
Yeah.
All right, see the film, so she'll film y'all walking out and she'll know, so you got to stay underneath the camera. All right, so part A here says, once again, worked this question quite a few times now. Here's a graph of f prime. Where does the function have a local min here? Last question we wanted to find a relative max. Now we're wanting to find a relative min. So what are we looking for here? Looking to see when f prime does what? If we're looking for a relative min, looking to see where f prime changes from negative to positive. So where does that occur up here? Where does f prime change from negative to positive? Okay, well, here's 5 right there. It's negative, f prime is negative here, okay, it's negative here, so it changes from negative to positive there. So hopefully we would say at x equals 6 is where that's going to occur. And the justification for that, as we said, it would be just f prime changes from negative to positive. Okay? What would we have there at 4? That'd be a relative max, wouldn't we? What about 1? Would we have anything at 1? Is that a relative? No, it's not. It's just f, the derivative is 0 there, isn't it? But we don't change from positive to negative or negative to positive. We just stay positive, positive. Part B says, on what interval would the graph of f be both concave down and decreasing here? Last time we wanted to find out where it was concave down and decreasing. Now we're wanting to know where would f be both concave down and decreasing. All right, so what are we looking for here? If we're looking to see where, say it again, where we're concave down and increasing. So in part B, we're wanting to know where f would be concave down and increasing. So let's talk about this. We know we're going to be increasing when f prime is positive. So here's when f prime is positive on these intervals right here. Now, if we want to know where we are increasing, which is what we do, that's what I've outlined in green there, that's when f prime is positive, and we want to be concave down, what are we looking for the concave down part? What does concave down mean for us?
The slope of f prime is negative.
F prime is decreasing, okay? So where is f prime decreasing? There, okay?
And right there.
And right there, okay? So we would hopefully say those intervals are going to be from 0 to 1 and from 3 to 4. And I'm sure it asks us to justify again, explain your reasoning. Once again, very similar to what we said last time, we're looking to find out when f prime is positive and what? And decreasing is what we're looking to find out there. F prime is positive, that's here, all these values above, and decreasing would be those two intervals there is what we have. And then that last part there, part D, is a little challenging here. All right, anybody get an answer there in part D? No? Just whooped us up? Okay. Let's look here and see if we can figure it out. See if I can. I'll get this, and let me go back here and do this real quick. Alright, so we're going to need both of these things here to kind of answer this question. Alright, so here's the graph. Once again, this is the graph of f prime, and then here is the question. It says the function g is defined by this. So here's g of x. We're told that f of 3 is negative 5 halves. Find the slope of the line tangent to the graph of g at x equals 3. So find the slope of the line tangent. What's that really asking us to do?
Take the derivative.
Take the derivative. I don't know why they didn't say that. They're just trying to confuse us. We want to find the derivative of g at 3. So ultimately what we're trying to find out here is g prime of 3 is what we're looking for. So if this is g of x, of course we need to take the derivative of that is what we need to do. So if I'm going to take the derivative of that, g prime of x here would be equal to, what rule are we going to use to take the derivative of that? Chain. So it's going to be 3 times f of x to the second power times the derivative of what's inside. What's the derivative of f of x going to be? F prime of x is what it's going to be. So that's our chain rule. And we're wanting to find the value of the derivative of this at 3, so we're going to plug in a 3 for x. Plug in 3 for x, this will be 3 times f of 3 squared times f prime of 3. Well, they've been nice enough to tell us that f of 3 is negative 5 halves. So right there, where it says f of 3, I'm going to plug in a negative 5 halves is what I'm going to do there. And we're going to square that. And then we got to multiply that times f prime of 3. Well, what's f prime of 3 here going to be?
4.
Very good. All right, don't make that any harder. What is this the graph of? F prime. We want to know the value of f prime at 3. What's the value of that f prime at 3?
4.
It's 4. Okay? So we're just going to plug in a 4 right there. That's what we'll do. Are you going to multiply all that together and square it? Are you going to? Hopefully not. What are we going to do? Leave it just like this. That's a free response question. Don't worry about getting an answer there. Leave it just like that and you'll get the full credit. If you try to simplify it, and I know it's hard for me, I'm kind of an OCD type person, the final answer is 75, but I don't want you to do that, okay? Because if you do and make a mistake, you're going to miss those points. All right, so we did a bunch of free response. All right, let's flip back then to our multiple choice and see what we can do. Hopefully we can get these down. Flip back to page 29 and do those two questions on page 29. Graph of f. Well, I would hope, this is kind of a test-taking tip here, guys, I hope we can do away with C and D quickly. We know if this was the graph of f, we know the derivative would not exist at 2 and 4 on this one. And you can see the derivative does exist at 2 and 4 there. And the same thing here. So these two are done. If this was the graph of f, the derivative would not have a value at 2 and 4. So we're done with C and D, hopefully right off the get-go. Now, so it's either got to be A or B. All right, so which one is it? Well, it's got to delve a little, got deeper into, dig deeper, goodness. and figure out what's going on 0 to 1. If this is the graph of f prime on the interval 0 to 1, what's the function doing?
Decreasing.
Decreasing, okay? Both of those are decreasing 0 to 1, so they're both in play. All right, what about from 1 to 3? What's the function doing? Increasing. All right, both of them are increasing, it appears, from 1 to 3. And then what about from 3 to 4, or really 3 to 5, really what we figure out. What's the function going to be doing on the interval 3 to 5?
Still increasing.
Still increasing. This right there is wrong, okay? That is decreasing. We see right here on the interval 3 to 5, the values are positive. F prime is positive, so we should be increasing. So hopefully you chose A for number 4. All right, we good with that? And then 5, all right, number 5 here, ask us, kind of once again, we kind of hit this a bunch of times. This is the graph of f though. We got to be careful about what graph they give us. It says the graph of the function is shown here. So this is f, for which the following values is f prime of x positive and increasing. So if that's the graph of f, if we want to know when f prime is positive and increasing, what are we looking to see here? Where this function is what? If f prime is positive, what's f got to be doing? Increasing. And if f prime is increasing, then what do we got to also know about f? It has to be increasing in what? Concave up. So which of these values over here are we increasing in concave up? A? No, we're decreasing. C? We're increasing, but we're concave down. So the only one of these where we're increasing and concave up would be E, is what we should have there. That should be our correct answer. Okay? Questions? Thoughts? Well, how you feel right now? Is this helping you guys any? All this a review for you? Have you heard anything new today? That's a good thing if you hadn't, really and truly. I hope that nothing's been new to you. Hope that everything you've heard, you've taught, has been taught, okay? May have been a while since you've had some of this, and that's kind of, if we don't use it, we lose it, right? But hopefully this has been kind of a review. Any questions or anything I've said, anything we've done? Y'all are all on it. Okay, let's try a couple others then. Flip the next page, 6 and 7. Y'all are about to rotate and get out of here, so you don't have to see me next section. Why you will make this work? Yes, sir. What'd you get, Norm?
I got B.
You got B. Okay. That's not what I got. What'd you get, bud?
C.
I got C. Okay. And let's check it. I know it's hard. This is a difficult question just because you got to think about all these different scenarios. If you looked at, let's go with what Noah said. Let's figure out why B is not it. If this was our function, okay, if this was our function, then we know that our derivative would be negative from negative whatever to 0, okay? So you said B, right, Noah? So that kind of rules that out right there, okay? Because if this was our function and that's our derivative, the value of the derivative should be negative on that interval, so we should be over here. Okay, does that make sense why that wouldn't be it? Okay?
Yeah.
Let's try C, okay? If this is our function, then our derivative would be 3. So as we said, the derivative, we're decreasing here, so our derivative should be negative. So far, so good. We're increasing here, so our derivative should be positive there. Okay, looks good. Then we're decreasing from here to here. Okay, looks good. And then we're increasing the last little way, so it's positive. That looks like the right way to go. And then you could just double check over there with that. So that's a little bit hard. I don't particularly like that question, but it's just because I think it's too many moving parts there. They can make that problem, to me, a lot easier, and you can still get the same concept. And then what about number 7? Number 7 here. Let me get down here. Number 7, this is the graph of f prime, which the following statements must be true. Must we have a relative minimum at x equal -3? If this is the graph of f prime, is that going to be a relative minimum?
Negative.
What do you think? Yes or no?
Yes.
Yes, that's true. F prime does what right there at -3? negative to positive. Okay, so that's true. The graph of 8f has a point of inflection at x equals -2. What do you think about that?
I say nay.
No, that's not true, okay? Where do we have points of inflection on the graph of f prime?
Extra.
Extrema, very good, or where f prime changes from increasing to decreasing or vice versa. That's not happening at -2. Where would we have a point of inflection if that's the graph of f prime?
On the board.
0.
At 0, okay, so that's not true. What about 3? The graph of f will be concave down on the interval from 0 to 4. Is that true?
Yeah.
Yeah, it is, because what's f prime doing there?
Decreasing.
Decreasing. So the only ones that have to be true would be 1 and 3, so make sure we circle the right answer. So E is what we would get. All right, I think that's 11:10 is what I've got. What time is it? 11:12. All right, any questions, guys? All right, best of luck to you guys. Hope you do well. Hope this has been beneficial for you some. Y'all are going to the next door down here for the last session. Y'all have a great rest of your day.
It says, if f is continuous on a closed interval, a to b, and f of a does not equal f of b, then for every value of m between f of a and f of b, there is at least one value of c in the open interval a to b such that f of c equals m. And you know, that's kind of how all that came through, didn't it? All we're looking at here is the point here at this end, the point here at this end, and every value in between. All this says is that if our function is continuous on a closed interval, we're going to take on every value between this y value and that y value. Now, notice the graph that we've got here, the function we've got here, actually goes outside of that. It doesn't matter. We're only worried about the values in between, and this is what's called an existence theorem. It tells you that the values exist. It does not tell you how to find them. So this is essentially one that, yeah, there's a number in there that's this number. Good luck going to find it. That's pretty much how it is. So this is primarily used just to say that the number's in there, and you can go and find other ways to find it. All right, the next one is the mean value theorem. And it says if f of x is continuous on the closed interval from a to b, and differentiable on the open interval from a to b, then there must be some value c between a and b such that f prime of c is equal to f of b minus f of a over b minus a. In other words, the instantaneous slope at some point in this interval is going to equal the average slope over that same interval. That's what we're saying. Now, make sure that you always understand this is an if-then statement, therefore what do we know? We have to know that the if part is true before the then part applies. If it's not continuous and differentiable, then the mean value theorem doesn't apply. So what we're looking at here, over here, all this is what? The slope formula, y2 minus y1 over x2 minus x1. And all we're doing is we're finding the slope of the secant line from one endpoint to the other. So that blue line right there is our average rate of change. And this theorem simply says that somewhere in this interval, we're going to have a tangent line that has exactly the same slope if the function is continuous and differentiable. So somewhere in that interval, we're guaranteed one. Now this one's not just an existence theorem, it actually gives us a method for solving it. We can actually find what this is, and then if we've got the derivative, or the function, we can take its derivative and find what value of c actually gives us that number. So this one actually gives us an equation to solve to find the value we're looking for. All right, and the last big theorem we're talking about is the extreme value theorem. And it says if f of x is continuous on a closed interval, a to b, then f of x has an absolute maximum and an absolute minimum value on the interval from a to b. This, once again, is one of those existence theorems. It says it exists, go find it. So looking at a couple of examples here, here is a continuous on the closed interval equation, or function. Where is our absolute maximum going to occur for that one?
highest point.
The highest point. In other words, at the top of the hill here. Where is the absolute minimum going to occur?
The lowest point.
The lowest point, which is going to be on the left endpoint here. So closed interval, we're guaranteed a maximum and an absolute minimum. What about here? Absolute maximum occurs, right endpoint. Absolute minimum, left endpoint. What about this one? Absolute maximum, right endpoint. Absolute minimum, left endpoint. What do we know about these? They're not absolute, but they are relative, yeah. So remember, the extreme value theorem is not talking about relative. It's talking about absolute. And we're guaranteed an absolute maximum and an absolute minimum on a continuous closed interval. So here, absolute maximum, absolute minimum. Where's the absolute maximum on this one? Top of the hill. All the way up there. Where's the absolute minimum? Can you have more than one? Okay, the thing is, think about this, when we talk about an absolute minimum, what are we talking about, an X value or a Y value? Y value, right? Because we're talking about the lowest. So the fact that we have a low value here and here, does that change the fact that that's an absolute minimum? No, it's still the lowest Y value, it just occurs what?
Twice.
2 times. So yeah, we still have an absolute minimum, we just have it occurring twice instead of once. All right, now the candidates test tells us how we can find the absolute minimums and maximums on a closed interval. The first thing you want to do is you want to find the critical values of the function in the interval. If you've got a derivative that is a fraction, you want to set both the numerator and the denominator of f of x equal to 0. Because what do we know? If we've got a function or a derivative that is a over b, when's that thing equal to 0? When is a over b equal to 0? When a is equal to 0. Remember, we can do 0 divided by anything, and we're still going to get 0. When's this thing going to be undefined? When b is equal to 0. So that's why you set both a and b, both the numerator and the denominator, equal to 0 to find critical points. Because remember, the critical points are where what? The derivative is equal to 0 or is undefined. All right, and then you want to evaluate f, the actual function, not the derivative, at each one of those critical numbers. And that's finding what the values at each one of the critical points are. Because remember that last example we looked at there, it did this number right here, well, sort of, kind of. And what do we notice with that one? Our absolute and minimums and maximums occurred at what? Critical point. That's a critical point, that's a critical point, that's a critical point. It didn't occur at the endpoints. So you want to check each one of your critical numbers in your function to find what its actual y value is. And then the last part, or part 3, evaluate f at each one of the endpoints. Because at the endpoints of a closed interval, like we had, you can have absolute maximums and absolute minimums. So you got to evaluate the endpoints as well. Once you have all those y values from the critical points and the endpoints, then here's the tough part. You look at them and see which one's the highest and which one's the lowest. Tough, huh? The smallest of these values is the absolute minimum. The largest is the absolute maximum. Now, guys, let me go ahead and tell you, about probably 4 years ago, I had a group of kids that were smart and they were, well, let me change that. They were okay. But about 2 days after the AP exam, your teachers get the questions are released, and we actually go over them in my class. So 3 or 4 days after the exam, we're sitting there, and I'm working a problem, one of the free response problems that they did on the AP exam on the test. And I work one out and find the absolute minimum, and it's at an endpoint. And I turn around to see 2/3 of the kids in my class with their heads down and their heads in their hands. And I said, let me guess, you forgot to check the endpoint. And they all nodded their head. So make sure if it's a closed interval and you're looking for absolute maximums and minimums, you check those endpoints. Because I guarantee you, if they've got one of those on the AP exam, the endpoint is gonna be a maximum or minimum because there are so many people that forget to check them. It's not just the critical points. It can be the endpoints as well. All right, now remember to discern and understand the difference between where the absolute maximum or minimum occurs as opposed to what the absolute minimum or maximum is. When they say where, they're looking for an x value. Where does it occur? They're looking for the x value. When they ask what the maximum value is, they're looking for the y value. Make sure you understand what they're asking because it makes it a lot easier to actually answer the question. All right, any questions so far? And guys, if you got questions, stop me. That's what you guys are here for. You're giving up your Saturday to learn something. Don't let me just ramble on and if you have a question. All right, so let's do some problems. The first one, a function f is continuous on the closed interval from 2 to 5, with f of 2 equaling 17 and f of 5 equaling 17. Which of the following additional conditions guarantees that there is a number c in the open interval 2 to 5 such that f prime of c equals 0? All right, so what do you see in here? You see this right here, what should go off in your mind? F prime of c should make you think of the... F prime of c is the mean value theorem. That's the left side of the mean value theorem, right? So anytime you see an f prime of c, you should think of mean value theorem. What has to be true for the mean value theorem to work?
Continuous.
Has to be continuous, check. But it also has to be differentiable. Now, if we were to go over here and assume that the mean value theorem applies, don't do that. But if we did, what would we end up with our average rate of change with 17 and 17 as our two y values? 0, right? We'd have 17 minus 17 on top, which would give us 0 over 3. So we need to know that this thing is differentiable as well as continuous. They tell us it's continuous, but we would need to know that it's differentiable. Do we need to know that it has a relative extremum on the open interval from 2 to 5? No, we don't. Matter of fact, is it guaranteed a relative extremum on that interval? Not necessarily. That's not going to help us. We definitely need something more, and that we haven't talked about yet. So it is C. Because the mean value theorem only applies if a function is continuous and differentiable. All right, number 2. We've got a table problem. AP loves using table problems. The table above gives values of a differentiable function f and its derivative at selected values of x. If h is the function given by h of x equals f of 2x, which of the following statements must be true? All right, now, with the first one here, h is increasing on the interval from 2 to 4. I'm going to read that just a little bit differently, and you should think about this every time you see an interval. H is increasing for every value between 2 and 4. Now, if I read it that way, does it change how you see it a little bit? Well, increasing over the interval from 2 to 4 just simply means it would be going up. If it's increasing for every point or every value between 2 and 4, what does that mean? The slope would have to be positive for every single stinking point in between 2 and 4. And what do we know about that? We don't have enough information up here to figure that out. So that one's going to be a false. Be careful about making assumptions of things in between pieces of information you have. Be careful about that. All right, there exists C over the interval from 0 to 4 such that h of C equals 12. Well, we're looking at f and f prime here. How do we find what h is? Well, h is f of 2x. So let's find h of 0, and let's find h of 4. Actually, let's go ahead and find all of them. Let's find h of 2 and h of 4 also. So h of 0 is f of 2 times 0. And what is 2 times 0? 0. What's f of 0? 3, right? Here's my x value, there's my f of x value. All right, what about h of 2? That means we're going to have f of 2 times 2, which is 4, and f of 4 is going to be 9. And then h of 4 means we're finding f of 2 times 4, or 8, and f of 8 is 13. All right, so right here, there exists a value c on the interval from 0 to 4 such that h prime of c equals 12. True or false? Okay, if we're going from 0 to 4, we're going from 3 to 13. What do we know happens when we go from 3 to 13? Somewhere in there, we're going to pass 12, right? Okay, what means that, what would you have to know that you're guaranteed that you're going to hit every value in between there and there? Intermediate value theorem, which means what's the qualifier for the intermediate value theorem? It's got to be continuous. Do we know that h is continuous? Well, it says differentiable. What's it talking about? The table above gives values of a differentiable function. So what's differentiable? F, right? Does that mean that h is continuous? Is differentiable? Yes, no, maybe, I don't know.
No.
Or, maybe, or, yes. Now, we've got a rule that you probably forgot about, but it says if we have a continuous function, and this applies to differentiability as well, if you have a differentiable function or functions, and you multiply them, add or subtract them, or do a composite with them, the resulting function is also going to be continuous or differentiable. That kind of comes back from Algebra 2 and pre-cal. But that means that if we use any differentiable function as a composite, we're going to end up with a differentiable function as well. Now, what was the one thing that you noticed, if you listened to it, that I left out of that list of things? I did product, addition, subtraction, and quotient. Never mind, I just gave away the answer. Quotient. Why would you not include quotient?
Because quotient has an S in
No, you sort of, kind of. What's the big thing that we're going to have problems with a quotient? Possibility of
0 in the denominator.
0 in the denominator. We cannot divide by 0 because what do we know? Well, the world implodes and people die. We can't do that. So don't divide by 0. It's bad. So we know that since this is just a composite of a differentiable function, this is going to be continuous as well. Therefore, intermediate value theorem applies. So that one works. All right, 3. There exists a c over the interval such that h prime of c equals 3. Well, once again, right there, h prime of c, that should set your spidey sense off because of the c thing. And h prime, mean value theorem. So give that a try. So if we do it over 0 to 2, that means h prime of c would have to equal what? H prime of 2, 9, minus h prime of 0, 3, over 2 minus 0. And what do we end up with? 9 minus 3 is 6, 2 minus 0. So what do we guaranteed somewhere in that interval? That h prime of c is somewhere going to be equal to 3, which means that what? That one would work. That would work if what? If h is differentiable and continuous, which we've already talked about why it is. So it's 2 and 3 only. All right, I want you guys to try this one. Let f be the function defined by f of x equals the natural log of x over x. What is the absolute maximum value of f? So see what you can come up with this. I'll give you about a minute and a half, 2 minutes.
Page
or undefined. Those are going to be the critical points, because what do we know about this instance right here? The extreme value theorem really doesn't apply, because what we know this is not. It's not over a closed interval. This is an open interval that goes on forever and ever and ever. We're looking for just the absolute maximum. So let's take the derivative. We've got f prime of x. And what do we got to use to find the derivative here?
Quotient.
Quotient rule. So we've got bottom times the derivative of the top. What's the derivative of natural log of x? 1 over x minus bottom d top minus top d bottom, natural log of x times 1, all over the bottom squared, so x squared. All right, so when we simplify this thing down a little bit, x times 1 over x gives us 1, of course. Natural log of x times 1 gives us minus natural log of x over x squared. So we're looking for where this thing is undefined. Where is it going to be undefined? When x equals 0. So x equals 0 is a possible. Now, I'm automatically going to turn around and throw that thing out. Why?
Because you're looking for the maximum value.
Yeah, but I'm looking for the maximum of y, and the maximum of y could possibly be at x equals 0. The thing is we're running into problems right there. What's the natural log of 0?
1.
It's undefined. Think about your natural log. That's not what I want to do. Can never, ever, ever take the log of a negative number. So remember, our graph of natural log looks like this. So it never exists where x is negative. And if you forget what that graph looks like, remember, it's nothing more than the inverse of what? The exponential, e to the x. So it's just that thing flipped across the line y equals x. So it's never, where this is never going to go into y values being negative, this one never goes into where x is negative. So those base graphs, they're important to remember because they help you to picture this stuff and put it in context. All right, so we know that x equals 0 will never be one of our solutions. So now all we're left with is what? The top being equal to 0. Because if the top equals 0, then this thing equals 0. So 1 minus natural log of x equals 0. Solve that, what are we going to do? We're going to move the natural log over, so 1 equals natural log of x. What's x going to be there?
1 over e.
All right, now let me show you a little trick here. 1 equals, I'm going to rewrite natural log as the log base e of x. And you guys remember how you take a log and you swap it over into an exponential? Well, I've got a little trick that I use. It's a spiral. You start with a base, go to the other side of the equal sign, and then come back over. So e to the first power equals x. So I can actually solve that by rewriting it as an exponential function. So my solution for x is x equals e. So what is x equals e? That's a critical point. Is that what we're looking for? Well, I hope not, because that's not one of the choices. What is x equals e? X equals e is the where. What are we looking for here?
How high?
The what. We're looking for what is the absolute maximum. How do you find that?
Plug that back on the original equation.
We do the Glade maneuver, and we plug it in, plug it in. Do what Glade tells you. So we're going to find f of e. So when we plug that in, we're going to do natural log of e over e. And what do we end up with? Natural log of e is 1, and e is, well, e. So b is our answer. All right, number 4, let f be a function that is continuous on the closed interval with f of 2 equaling 10, f of 4 equaling 20. Which of the following is guaranteed by the intermediate value theorem. I want you guys to read through that and give that one a try. All right, number A, or part A, f of x equals 13 has at least one solution in the open interval from 2 to 4. F of 3 equals 15. F attains a maximum in the open interval from 2 to 4. F prime of x equals 5 has at least one solution in the open interval 2 to 4. F prime of x is greater than 0 for all x in the open interval from 2 to 4. Now, which ones can we toss out automatically? Having to do with the intermediate value theorem.
D and E.
Yep, D and E. Those would have to do with what? Mean value theorem or just plain derivative. So we can get rid of that one and that one. And looking at these, which ones are guaranteed? Which one is guaranteed? Only one of them is, by the way. A. Why A?
Because it doesn't state a specific point, it just says it'll hit 13 on that line.
Exactly. F of 3 equaling 15 is way too specific. It says that when x equals 3, y equals 15. We don't know that. If it was a linear function going from 10 to 20, then yeah, it would work. But this is very specific, and it could be doing anything in between these 2 points. So we know that one doesn't work. F attains a maximum on the open interval. Well, from the intermediate value theorem, doesn't tell us anything about maximum and minimum, but even the extreme value theorem says what? It could occur at the endpoints. So you're not going to have a maximum on an open interval guaranteed. So A is the only choice. All right, F is continuous for the interval from A to B, the closed interval, and differentiable over the open interval from A to B. Which of the following could be false? All right, could A be false if our function is continuous and differentiable on these intervals?
No.
No. Why? What do we call that?
No.
We call that the mean value theorem. And that's kind of hard for it to be untrue and false over if it's qualified. And it's qualified with continuous and differentiable. What about B? F prime of C equals 0 for some C. Well, we don't know anything about what the values are, do we? We don't know that we necessarily have a horizontal tangent anywhere along through there, so we don't know that that's true. It could be false. So this one definitely not. This one could be false. So maybe. F has a minimum value on the closed interval from A to B. Could that be false? Well, what does the extreme value theorem say? It says if we have it continuous on a closed interval, what do we guarantee? An absolute maximum and an absolute minimum. So F has a maximum and a minimum value, so both of these cannot be false. And what about this last one? Well, let's ignore that one because we haven't talked about integration yet. So it's going to be B. B is the only one that could be false. Does it say that it's guaranteed to be false? No, it says it could be. All right, the function f is continuous on the closed interval 0 to 2 and has values that are given in the table above. The equation f of x equals 1/2 must have at least 2 solutions in the interval from 0 to 2 if k equals what? Now, a little piece of information here. The equation f of x equals 1/2 must have 2 solutions simply means this. It means the y value is going to be 1/2 2 times. A lot of people get thrown off by that, but that's all that says. So now, looking at this, let's get some points here. We've got 0, 1, and we've got 2, 2 over here somewhere. And somewhere in here we've got a value of 1. And it says, what value must k have to guarantee 2 solutions? Well, to have that solution, to have 2 solutions, that means it's going to have the value of 1/2 twice. So let me draw a line in here. There we go. And we'll call that y equals 1/2. So now, if let's start at the other end. Let's start with 3. If k is 3, so we have the point 1, 3, are we guaranteed that we have to cross this line twice? No, it could go up there and then come back down, never cross that once. What about if it was 2? Nope, it could go up there and go straight across, never have to touch that line at all. 1, same thing. It could go over here and then go up there, never touch that once. What about 1/2? It can go down and touch it one time and go up there, and it only has a solution where f of x equals 1/2 one time. But if it goes down to 0, then we guarantee that it has to cross it once to get to 0 and once to get to 2. So that is just a backwards application of the intermediate value theorem. All right, let f be a function that is differentiable in the open interval from 1 to 10. If f of 2 equals -5, f of 5 equals 5, and f of 9 equals -5, which of the following must be true? I want you guys to try this. Go through 1, 2, and 3, and with that piece of information, it's differentiable, and what do we know if it's differentiable? It's also continuous, so we know it's continuous and differentiable on this interval, and I want you to tell which ones of those must be true. All right, does f have at least 2 zeros?
It has to,
Has to. Why?
because it goes positive to negative, then negative to positive.
It goes negative to positive and positive to negative, and by which one of our theorems tells us that we have to have 2 zeros? Intermediate value theorem, because we're going changing signs, right? And it's differentiable and thus continuous. So it is continuous, and it goes from negative to positive and positive to negative, which means it crosses 0 2 times. Yes, that one works. Check mark there. The graph of f has at least one horizontal tangent. Also true, and with that case, we're starting at -5, we go up to 5, and we get back to -5, and since it's differentiable, it has to be smooth, so we can imagine this as some curve that I can't draw, evidently. So it's going to be guaranteed to have a horizontal tangent somewhere. Now, it doesn't have to look like that. It could easily do this number here, or anything crazier than that, but it's guaranteed since it starts at -5 and ends at -5, somewhere in there it has to have a horizontal tangent. So yes. And by the way, have you guys heard of Rawls' theorem? That's a specific case of the mean value theorem. That's where the beginning y value and the ending y value are the same, and it just guarantees a horizontal tangent somewhere in there. All right, in part 3, for some c in between 2 and 5, f of c equals 3. Yes or no? Must it be true? Okay, if we're going from 2 to 5, x values, we're going from what? -5 to 5, y values. And what do we know? It's continuous. Intermediate value theorem says it has to take on every value between -5 and 5. In case you didn't know that, 3 is in between -5 and +5. So that one works too. So all 3 of these are true. Must be true. Any questions on this? All right, so let's do some free response questions. The functions f and g are differentiable for all real numbers, and g is strictly increasing. The table above gives values of the functions and their first derivatives at selected values of x. The function h is given by h of x equals f of g of x minus 6. Explain why there must be a value r for the interval from 1 to 3 such that h of r is equal to -5. Alright, so we're dealing with h, so we're going to need to find some values of h here. So let's go ahead and work those out. Let's do h of 1 and h of 3. Now, if we do h of 1, that means we're going to end up with what? F of g of 1 minus 6. And what is g of 1? G of 1 is 2, so in place of this thing in here, I'm going to put a 2. And what is f of 2?
9.
F of 2 is 9, so we end up with 9 minus 6, which gives us 3. So h of 1 is 3. All right, and let's find h of 3. So we're going to find f of g of 3 minus 6. What is g of 3? 4. And f of 4? Negative 1. So negative 1 minus 6 gives me negative 7. All right, so there are 2 points on our graph at 1 and 3. So we know f and g are differentiable. What does that mean about h?
That it has to be differential?
It's differentiable also. Why? Because it's a composite of 2 differentiable functions. And that means that if h of x is differentiable, it's also continuous. And if we've got continuous going from 3 to negative 7, what do we know we're doing? Taking on every value between those two. Does negative 5 fit in there? It does. So now, how do we go about justifying it?
Intermediate value.
But let's go ahead and explain it. Because they want you to explain it, so we need to put it in our own words. Why must there be a value? Well, since h of x is a composite of 2 differentiable / continuous functions, it is also continuous. And h of 1 equals 3, h of 3 equals 7, and by the intermediate value theorem, h must take on every value between those 2 values over the interval from 1 to 3. And that will be enough for your justification. When they ask you to explain or they ask you to justify, they're asking you not necessarily just to do this work. This work is not enough to justify. That's your evidence that you're using. What you're doing is you're explaining why you know what you know. Because the whole thing, remember, they're talking about giving you college credit for this. So you got to justify that you understand it well enough to do your college credit, to get the college credit. So they're going to ask questions where you have to explain things. All right, part B, same problem. Says explain why there must be a value c on the interval from 1 to 3 such that h prime of c equals 5. Negative 5, sorry. Now, what should this one kick off? Again, we've got h prime of c. When you see a derivative like that, one of the first things you need to think about is the mean value theorem. So with the work we had before, remember we had h of 1 equaled 3, h of 3 equaled negative 7. So when that part right there comes up, I'm thinking, what is the right side of that equation? So h of 3 minus h of 1 over 3 minus 1. What do you end up with there? Negative 7 minus 3 over 2, which gives you negative 5. So now, if the right-hand side equals negative 5, what does that mean about the left-hand side? Remember, the mean value theorem, plugging in h's means that h prime of c would have to equal h prime of 3 minus h of 1 over 3 minus 1. Well, we've already proven that that equals negative 5. So that means that h prime of c has to equal negative 5 also. So how would you go about justifying or explaining that? Well, since h is differentiable, and continuous, the mean value theorem applies, And since the average rate of change over 1 to 3 is -5, then h prime of c must equal -5 for some value c in between 1 and 3. All right, questions on either one of those parts? So there's the math, but you've got to be able to put it in your own words there to be able to explain what you know and why you know it. All right, free response number 2. This is without a calculator. So a continuous function f is defined on the closed interval from -4 to 6. The graph of f consists of a line segment and a curve that is tangent to the x-axis at x equals 3, as shown in the figure above. On the interval from 0 to 6, the function f is twice differentiable, with f double prime of x being greater than 0. Is f differentiable at x equals 0? First of all, answer that question. No. Now, we've got to be able to explain in some way why we know that it's not differentiable at x equals 0. And they specifically give us the way why, or the way to go. Use the definitions of the derivative with one-sided limits to justify your answer. Now, you can get by, so we know the answer is no, and using our limits, one-sided, we're going to do the limit as x approaches a, definition of the derivative. I'm using the second one, and that's going to be f of x minus f of a all over x minus a. You can use the other one. This one's a little easier to use. Now, this is the, if you remember, this is the definition of the derivative at x equals a. So in this case, we're going to change this a to 0. And we can do a 0 here, and we can do a 0 here. Now, but more specifically, here's what I want you to do. What is the answer to this? Well, all we're doing here, if we're approaching this thing from the left, what's the slope over here? We could calculate it. We could use this point and that point and find what the actual answer is. But I'm going to make it even simpler. We just know that that thing is positive. So the slope on the left side of 0 is positive. Then we can do the exact same thing with the right side of 0. So the limit as x approaches 0 from the right of f of x minus f of 0 over x minus 0. And over here, what do we know about the slope? It's negative, right? So if the slope, as we get closer and closer to 0 from the left, is positive, and the slope as we get closer and closer to 0 from the right is negative, what do we know about this limit right here? Is that limit going to exist? No. If we're approaching two different values with a limit, we know that the limit doesn't exist. Well, if the limit of the definition thing here doesn't exist, what do we know? The derivative doesn't exist. If the limit that defines the derivative doesn't exist, then the derivative doesn't exist. So, since the limit as x approaches 0 does not exist, then the derivative does not exist at x equals 0. Now, what does it mean about everywhere else? Well, the derivative exists everywhere over here, everywhere over here. The only place the derivative does not exist is right there. And that's because the limit from the left and the limit from the right did not equal the same value. Remember, it has to be nice and smooth, and we can notice everywhere else that the the slope transitions. Right here, the slope is transitioning, negative, negative, negative to 0 to positive. It's a nice smooth transition. Here, we have that sharp change. That means the derivative doesn't exist. All right, for B, for how many values of A on the interval from -4 to 6 is the average rate of change of F on the interval A to 6 equal to 0? Give a reason for your answer. So if the average rate of change is equal to 0, what does that mean has to be true? If the average rate of change over an interval is equal to 0, what has to be true? The top would have to be 0, and what's the top doing? Finding the difference in your y values. So that means your y values would have to be the same. So what you can do with this graph is you can actually start over here at 6 and just draw you a line backwards. So now, anywhere that the function touches that horizontal line right there, I have a y value that's equal to the y value at my endpoint here. So that means if I found the average rate of change between here and there, what would my average rate of change be? 0. If I found it between here and there, it would be 0. So that's all you're looking for. So how many places, how many values of A would the average rate of change be? 0? 2. What's the reason for your answer? Well, there are 2 places where the y value would be equal to the y value at 6, or when x equals 6, giving us an average rate of change of 0. That would be enough for your justification. All right, now, is there a value of A over that same interval for which the mean value theorem applied to the interval A to 6 guarantees a value C for which f prime of C equals 1/3? Is there any value A that we can actually use there where we could have a value of 1/3 for our average rate of change? Well, what do we know about all the values over here? We can go ahead and exclude those because what? If we choose any value over here, we know that the mean value theorem will not apply because what do we know? It's not differentiable on our interval. It's not differentiable right there. So we're limited to only look over here. So we're looking for a place where we have a slope of 1/3. And what do we know is going to be true? Well, that would have to mean that we would have to have a situation where we had an increase in 1 and a run of 2. Well, guess what? From right here to right there, what do we notice? We go up by 1 and we go over by 3. So from there to there, we actually do have a value where we would have a slope of 1/3. So somewhere in the interval from 3 to 6, we're going to have a derivative that is equal. It does not apply over here, but remember, we're defining what the length of our interval is because we're choosing A at some point along the way. We just can't choose any A that's over here because the mean value theorem doesn't apply. So don't be careful and don't get thrown out by the fact that if I choose a value over here, that's not differentiable. If I choose just over here, any interval over here, mean value theorem still applies because I don't have a point of discontinuity, a point of non-differentiability in that interval. All right, let's look at one more and then we'll call it a day. All right, Ben rides a unicycle. back and forth along a straight east to west track. The twice differentiable function, b, models Ben's position on the track, measured in meters, from the western end of the track at time t, measured in seconds from the start of the ride. The table above gives values for b of t and Ben's velocity, v of t, measured in meters per second at selected times of t. Use the data in the table to approximate Ben's acceleration at time t equals 5 seconds. Indicate units of measure. Now, if we're approximating acceleration, what is acceleration?
It's meters per second per second.
Meters per second in this case. More specifically, what is it the rate of change of?
Change in velocity over
The
time.
rate of change of velocity over time. So what we're looking for here is we're looking to estimate what the acceleration is at t equals 5. So we're going to use the velocity and find the average rate of change of the velocity over this interval of time. So the way we would go about doing that would be using these values right here and these values right here. So A prime of 5 is going to be approximated by doing what? V of 10 minus V of 0 over 10 minus 0. Now guys, you need to show where these answers come from. You can't just, even though it's something that you could probably do in your head, make sure you don't just do it in your head and write down the answer. I'm kind of offended when they say this, but they don't accept what they call bald answers. Go ahead, laugh. But they don't take answers where there's nothing to support it. That's what they call a bald answer. So you've got to actually have the setup and have what you end up getting at the end. So V of 10 is 2.3. V of 0 is 2.0. And then over 10, so that's going to give us 0.3 divided by 10, which gives us 0.03. And that would be in meters per second squared. All right, for the interval from 40 to 60, there must be a time t, must there be a time t when Ben's velocity is 2 meters per second? Justify your answer. So we're looking for the velocity being 2 meters somewhere in the interval from 40 to 60. Well, from 40 to 60, it goes from 2.5 to 4.6 for the velocity. So looking at this, just the intermediate value theorem, what do we notice? Yeah, we don't think so. But there's other ways to do this. Remember, what do we know about velocity? It's also the derivative of the position function. So before just saying no and looking here and going, well, there's no 2 between 2.5 and 4.6, you also want to go up here and check this part using the mean value theorem. So with the mean value theorem, V of some value C would have to equal B of 60 minus B of 40 over 60 minus 40. Now what do we know happens there? B of 60 is 49, B of 40 is 9, 60 minus 40 is 20, so we end up with 40 over 20, which equals 2. What does that mean? That means we're guaranteed somewhere in this interval from 40 to 60 that V, which is B prime, would have to equal 2. All right, any questions on either one of those? All right, that's the end of that one, so we'll not work on that last one. You guys have been, quote, punished enough, I guess. You guys got any questions about anything that we've talked about, either here or you guys talked about over there? All right, if not, you guys are